In a previous video, we graphed data values in a scatter plot, and based on the scatter plot, we assessed whether there was a linear trend in the data. Now, if we have a set of data that has a linear trend, we can find what is called the least squares regression line, and that is also known as the line of best fit. Let's go over how you would find this equation for the least squares regression line through a set of data values. So we've been given a list of ordered pairs in a table, and we can calculate from those list of x values, we can find the sample mean. Now, how would you find the sample mean? You would add together all the x values and divide by how many x values there are. We could also find the sample mean for y, so add together all the y values, divide by however many y values there are. Now, we know how to calculate standard deviations, but we also know that's a rather tedious process by hand. So as we've already had practice calculating it by hand, for this section, since it's part of a larger problem, let's instead calculate the standard deviation of the x values and the standard deviations of the y values using technology, and we'll talk about how to do that in a little bit. Okay, we also need to find the correlation coefficient that was discussed in a previous video. Then if we have all of this information, then the line of best fit is y hat is b subscript 0 plus b subscript 1 times x. So here x is our variable, it's different values of x. And then y hat, the reason we're using y hat instead of y is we're not going to say that this equation exactly gives us the y values because, again, the data is not exactly a straight line. But it's a close approximation, so think of y hat as like our predicted or our approximated value. Now, what is b naught? B naught can be found, or excuse me, we first need to find b1. b1 is what we multiply by the x. That's the slope associated to the line. And it is calculated by the correlation coefficient times the standard deviation of the y data values divided by the standard deviation of the x data values. Once we have b subscript 1, that then allows us to find b subscript 0, as b subscript 0 is the sample mean of the y values minus b1 times the sample mean of the x values. The final thing I want to draw our attention to is the phrasing here. It says we're predicting y from x. So from x values, we're predicting the y values based on the trend set in the data. We have a particular name for the variable that we're predicting and the variable that we're drawing from. The variable we want to predict is the outcome or response variable, and it's represented by y. The variable that we're given is the explanatory or predictor variable, and it's given by x. Now, we mentioned earlier that part of finding the least squares regression line is doing two different standard deviation calculations. If we were to do these two different calculations by hand, it would take an immense amount of time. So instead, you've got two options. If your calculator has a lot of statistics capability built in, you could use your calculator to find the standard deviation. If your calculator is a simple calculator like the ones I've been working with in the video, you can instead use an online calculator, and you can have this online calculator open during your homework and our online exams. One recommended online calculator can be found here. We've got the hyperlink in our class notes, and this will be what I'll use in our upcoming example. Now, if you remember back to a previous video, we worked in creating a scatter plot based on the proficiency of 8th grade students who were proficient in reading and proficient in math. So we already drew our scatter plot for these data, and we already found the correlation coefficient. You can look back a few pages previous in your notes to find that example. We are now asked to compute the least squares regression line for this set of data. Now, the first thing I'm going to bring up is the general formula for the least squares regression line, so we know what are the aspects I need to find separately so that I can find this all together. So here I've just copied down the formula. here's my regression line. In order to find b sub 0, b sub 1, I need to find the correlation. I need to find the standard deviation of the x values, the standard deviation of the y values, and I need to find the sample mean of the y values, the sample mean of the x values. Now I have this data typed in from when we worked this example previously, and if I press calculate, I see the correlation when I round to 3 decimals is 0.809, so let's round that. The next thing that I need to find, because I have to find b sub 1 first, so that I can then plug b sub 1 into b sub 0. So we found the correlation coefficient. I next need the standard deviation for x and the standard deviation for y. I will have to calculate that separately. Now in this standard deviation calculator, I'm just going to type in my data values in a list. So for instance, I will let the proficiency in reading, since that's what we're taking our data from, that is our x value. So pay attention to how it's phrased. We're trying to predict proficiency in math. That's what we're trying to predict. That becomes our y value. So as I try to find the standard deviation of the x values, I'm just going to type in the data values that are associated with proficiency in reading. And I really need to make sure I don't type in any errors here, so I'm going to verify 60, 73, 75, 66, 75, 79, 79 again, 73, 67, 71. Once you've double checked that you've typed it in correctly, we will press calculate. And then this calculator gives you a lot of values. We need to be careful. Do you see here we've got in bold population standard deviation, sample standard deviation, and you see they're different values. Keep in mind, this is a sample of values. This is taken from 10 different states. So we are always in this case looking for sample standard deviation, and that's why it's written S subscript X instead of sigma subscript X. So if you use these online calculators and you're given both population and sample, keep in mind you must choose the sample value. Now rounding that to 3 decimal places, I get 5.996. And nicely, I notice I was already given the sample mean 71.8, so I'll write that down as well. X bar. Next, we just repeat the process for our y data values. So we type this in again into our calculator or our online calculator. And here, let's just verify we've got 59, 78, 70, 68, 70, 77, 76, 66, 64, and then 73. We'll press calculate. Now, if you would, from this list, identify what is our S subscript Y, what is our Y bar. We know we choose the sample standard deviation, so rounded to 3 decimal places at 6.100. And then our sample mean, keep in mind they're just calling it X. They don't know that this was actually our Y value, but I do see it's the mean. This would be 70.1. We'll record both of those. And now we have everything we need to calculate b sub 1. B sub 1 is 0.809 times the fraction. Make sure your standard deviation from the y values goes at the top, so that's 6.100 divided by standard deviation from the x values, 5.996, and that will be, when rounded to 3 decimal places, 0.823. Now that we know this value, we can use that along with our x bar and y bar to find b sub 0. It will be the y bar value of 70.1 minus the value we just found times the x bar value of 71.8. We'll calculate that. And we would get to 3 decimal places 11.009. Now do keep in mind, if you used a calculator to find this, your calculator did not round at this point or these points. So your overall calculation is going to be more exact than mine, which rounded at a few different points. but it is close enough. So if you have slightly different values and you use the calculator, it's because your calculator never rounded at approximate steps. So just keep that in mind. So we know that the least squares regression line is then y hat is equal to my value 11.009 b sub 0 plus b sub 1 0.823 times my variable x. So keep in mind, if you're asked to find the least squares regression line, as long as you know how to calculate these separate concepts are x bar, standard deviation of x, y bar, standard deviation of y, correlation coefficient, and you know the general formula, you can put it all together. Now keep in mind, what does the least squares regression line look like in a scatter plot? Well, the data points, unless they're exactly linear, are not going to perfectly fit on the least squares regression line. However, the least squares regression line is the best linear fit to the data. So although it's not an exact representation of every data point, it does give us a good approximation of the trend inside the data. And because of this, we can use the least squares regression line to predict the value of the outcome variable if we're given the value of the explanatory variable. How do you do this? You simply substitute the x value into the equation of the least squares regression line, and then the result, that y hat value, is the predicted y value. Now notice we say predicted y value because we are not sure that the least squares regression line models every data point perfectly, but it is a predicted estimated value based on the trend in the data. So let's look at this next example. It says, at the final exam in a statistics class, the professor asked each student to indicate how many hours he or she studied for the exam. After grading the exam, the professor computes the least squares regression line for predicting the final exam score from the number of hours studied. Now, one of the things we need to get from this example is tiny phrasings. They said, we're predicting the final exam score. That's your y value, y hat value. That's your predicted value. And you're predicting it from number of hours studied. That's my x value. The equation of the line given that they found was y hat is 50 plus 5 times x. Now it turns out Andy wrote down that he studied for 6 hours. What do you predict his exam score to be? Now, I'm not certain that his exam score is given by this equation. However, it is the best that I have to represent the data because it is the best fit through the scatter plot. So what I'll do is I'll say my predicted value follows the line of best fit when x is now 6. Now this begins 50 plus 30, so his predicted score is an 80 on the exam if the line of best fit is accurate through this data point. Now, depending on your background, you might have dealt a lot in the past with straight lines. We notice our least squares regression line is a straight line, and if we recall back anything to our previous algebra classes, you might remember the phrase y equals mx plus b, and from that we highlighted that b was the y-intercept and m was the slope. Now, what does our least squares regression line look like? Well, it is y hat is equal to b naught plus b1 times x. Now, the only difference between the two equations that I've written at the top of the screen is just a labeling difference. In your basic algebra classes, we like to talk about the slope being m, the y-intercept being b. For our statistics class, however, the y-intercept is this b naught. It's the value that we're just adding to the equation. The slope associated with the straight line is the value that's getting multiplied by the x. Now, the only reason I bring this up is so maybe if you've had experience with this in the past, this is something you can connect and build on, so you can quickly at a glance identify the slope and the y-intercept. So for my least squares regression line, my y-intercept is b naught, because it's the term I'm just adding to the equation. What's representing my slope is b sub 1, because it's what's being multiplied by x. And that's basically what we have written here. For the least squares regression line, the y-intercept is b sub 0, which is found by the term that you're just adding to the equation. And it's the point on the line where it will cross the y-axis. Now this will have a practical, what we mean by practical is in the context of the problem interpretation, only pay attention to this when the data contain both positive and negative values of x. So in other words, you can only give an interpretation to the y-intercept if your scatter plot contains both points before the y-axis and after the y-axis. Said another way, we could say if the data contain both positive and negative x values, then the y-intercept is the estimated outcome when the value of the explanatory variable is 0. Now keep in mind this caution. If the x values are all positive or instead all negative, the y-intercept does not have a useful interpretation, because that would involve extrapolating past our data values, because we only have positive or we only have negative, we don't have values that go through 0. Next, we'll interpret the slope. If the x values of 2 points on a line differ by 1, their y values will differ by the amount equal to the slope of the line, which is our b1, the value that's getting multiplied by x. Now this is a helpful explanation if the difference in x values is only 1, but what if the difference in x values is a larger value? For instance, if the difference in, they say, the explanatory variable, that's our x, if the values of the explanatory variable differ by d, then their predicted values, our y hat values, differ by b sub 1, the slope, times d. And that follows exactly from our understanding of how the slope works in a straight line. If you differ by 1 and you go up b1, then if you differ by d, you go up d times b1. So we've got the example that we just saw on our previous page. We've got the same line that estimates based on how long a student's been studying their predicted exam score. We do not know Emma or Jeremy's study time. We don't know how long Emma studied, we don't know how long Jeremy studied. Now, while we don't know those exact values, it does tell us a relationship between those values. We know Emma studied 3 hours longer than Jeremy. It says, how much higher do you predict Emma's score to be? Well, we can answer that from here. The amount of difference in their x value time spent studying is 3. And since this is a linear relationship, if the change in the x value is 3, then for each 1 increment change in the x value, the y value goes up by 5, the slope. So my predicted difference in scores will be 5 times 3, or 15 points higher Emma's score compared to Jeremy's. Now, we do need to put in the phrase predicted, because of course this is just predicted. We know hours spent studying does not necessarily guarantee a higher score. It might oftentimes be associated with one, but it's not a I do this, I get this automatically as a result. So we'll just clear this up by saying Emma's score is predicted to be 15 points higher than Jeremy's. Now, keeping in mind what we saw on the last page, it told us when we could predict what the y-intercept represented in a scatter plot. And remember, you can only interpret the y-intercept if you had x values that were positive and negative. So for the 2 graphs that you see given here, our first graph, our second graph, answer the first question of, can we interpret the y-intercept? What are you looking for? In both cases, I'm looking for, are there positive and negative x values involved? And I see here I've got negative x values, I've got positive x values, I've got 0 in my range. So here I can give an interpretation to the y-intercept because the x value that generates the y-intercept is included in the data values. X equals 0 is present in the data. Now looking at the next data values, we see that we only have 4 to 12 listed, only positive x values. Since there's only positive x values and not also negative x values, we know that we cannot interpret the y-intercept for this scatter plot because it lies outside the range of data values. Now we're not quite done yet. The problem did state that if we could, we need to interpret it, not just could we interpret it. So let's quickly go back to our explanation of how we interpret the y-intercept from the previous page. So here we read the y-intercept is to be interpreted as the estimated outcome when the value of x is 0. So the only thing I need to do to finish up our example is put things in context of the problem. And I'll do that by looking at my axes to see what are we measuring in the x-axis. That's when x is 0. And then what's that predicted value that we'll see in our y-axis? What is it representing? So as I'm answering this, I would say my general start, the y-intercept is the expected, so remember, or expected or predicted y value is time to freeze. Here we're freezing some amount of material. Time to freeze, and then the units are in hours, so I'll say in hours. This y value occurs when x is 0. So I need to say, what does x represent? Well, x is the temperature in Fahrenheit, and we're interested when x is 0. So when the temperature is 0 degrees Fahrenheit. And that will be my interpretation of the y-intercept in this example. So as always, if you have questions about the material, do reach out to me via our campus communication, and I'll be very happy to help you.